example. So I'm not really even going to give you guys time to go through and do this one. So that carbon is a chiral atom. So we want to go through and determine if it's R or S. Okay? So I went through as a first tier and did in red the first atom connected. So we have oxygen and then 3 carbons. Well, because oxygen has the higher atomic number, that one is now a 1. Between the other carbons, I can't directly differentiate, so I will move to the next highest priority atom out from each of those, which I then highlighted in purple. Okay? So we've got a purple carbon, a purple hydrogen, and then a purple carbon. Hydrogen has a lower atomic mass than the carbons, so that means that bottom one must be our 4th priority. So far, so good? If we then move to the next 2 carbons, the next furthest out for our highest atomic number would be the oxygen in blue versus the hydrogen in blue. Oxygen is a higher priority than hydrogen, which then means, if we track all the way backwards, this one is our highest priority. Whoops, next highest priority, which in this case would be a 2, followed by 3. This example was picked for a couple other reasons too, because if we compare 1 to 2, position 2 has more mass. There's 2 carbons and an oxygen. Position 1 just has 1 oxygen. Okay? Position 1 still gets the higher priority because oxygen is a higher priority than carbon. It is literally the atom that is directly connected. That is where I make that differentiation. Once I've made that differentiation, I move on. Okay, kind of makes sense? I got one head shake yes, so we'll accept that. If I look at this structure, the thing that becomes tricky on this one, where is the lowest priority located? At 4, it's in the plane of the paper. To assign R and S, that must be moved or oriented in such a way that it is away from the viewer. Okay? That means we're looking at the molecule from the wrong direction and we would have to make an adjustment. Okay? This is where it requires rotating the structure. If you've been good with models, okay, or if you built a model and you're set already, you've got, say, a red ball, a blue ball, a green ball, and no ball, you could then go through and change your orientation on that and nail down what the R or S assignment is without actually having to draw out those rotations. I always found R and S difficult because I have to draw them all out. Only recently have I gotten good enough at it that I can kind of nail it down by changing my viewpoint and pretending where I was within that 3-dimensional system. Okay? So what do I mean by changing the viewpoint? 4 has to be aimed away from me, which means if I'm going to draw an eyeball in here, I need to be, there's my eyeball. Oof.
That's a very scary.
Wow. I don't think I can make it better. But there's an eyeball looking in that direction. Okay? Completely opposite the 4. Which means if I went through and did that rotation, I'd be rotating 1, 2, 3 towards my right, and that would be clockwise, and that would be assigned R. Right? That doesn't mean I'm right, because I didn't do any of the redrawings, and that usually means I screw it up some way or another. Right? So how to do the rotation? I want to rotate about that bond, but I actually want to rotate the other direction. Because what I'm trying to do is get that position 4 to rotate backwards. Everybody kind of see that? So if I were to draw that out, my position 2 does not move because I'm rotating about that bond. Okay? Position 4 rotates backwards, which makes it now dashed. Okay? Where does the oxygen then go? Position 1 rotates out front. There's 1. There's 3. 1, 2, 3. Oh my God. It's the first time for everything. And there's the R. Okay, everybody see that? Okay. Again, Assigning RNS, there are tips and tricks on the internet. If you can get them to consistently work, by all means, go ahead and continue to use them. My success with anything where position 4, our lowest priority, isn't aimed directly away from me, have been awful. Okay, so if position 4 is in the plane of the paper, I pretty much screw it up every time. Okay, and I have to draw everything out. Okay? There is one exception to that. If 4 is aimed at me, it's also really easy. Okay? If 4 is aimed at me, I'm just looking at it backwards. So I'll just do the 1, 2, 3, whatever it's assigned, and then just make it opposite of that. Remember, that was the whole which way is my hand moving, and we just turn around. Okay? So if it's aimed at you or away from you, it should be really straightforward. If it's in the plane, that's one of the trickier ones. You have to be a little bit more careful with that assignment. As long as you get it correct, I'm okay with it. Realize again, it's a coin toss, 50-50. Okay? Make sure that you're better odds than 50-50. Okay? At least before the exam hits. Kind of make sense? Okay. Which is about to get us into the next part. Recording. IR. OH, CH, SP3. Mass, that's the wrong button. Let me try that again. Mass spec, that peak is important at 93. Oh, because it's odd nitrogen. I may have counted that wrong too. 1, 2, 3, 4, 5, 6 peaks. Alkane. Carbon-carbon style, potentially aromatic, or likely aromatic. 1, 2, 3, 4, 5, yeah, 6 peaks. HNMR. We have 1, 2, 3, 4 peaks, or 4 signals, I should say. After that, I'm not even going to bother to interpret. Okay? That speed is insanely fast. You should be getting that information down minimally right away. That needs to be used and controlled because all of that was useful information that you can use to answer the question. Okay? Every single bit of it. Okay? So make sure you're getting better at coming up with that information fast. You are not fully expected to be able to interpret yet. Arguably, by Friday, you should have been able to solve at least a couple spectra problems, full spectra problems, out of that spectroscopy packet that is posted on Canvas. Okay? If you're not in lab, you're not required to complete any of that spectroscopy packet. It is still highly encouraged that you go through and do so because your instructor is insanely lazy. So, moving on, RNS. We can get an alternate view with Fischer projections. Okay? Arguably my least favorite way to look at a molecule. The more I have to talk about it, the more it actually looks kind of fun and interesting and kind of like a punching myself in the face way. This ultimately centered on biochemists looking at carbohydrates. Carbohydrates are a lot more complicated than your standard organic molecules that we look at because they have a lot more chiral atoms within them. This makes it more difficult to come up with a name. For instance, to name this structure, we would have to address that we have 1, 2, 3, 4 chiral atoms. So at the very beginning of our name, we're going to have this string of 1R, and I have no idea what they are, so I'm just making this up. 2R, 3R, 4R. How did I say 4 of them? 1, 2, 3, 4. Let's make the fifth one S. That's just to start the stupid name. Now we could go through and actually name the rest of the structure with all those alcohols, the aldehyde, and all that fun stuff. Right? So it is not a fun way to go through and deal with name, even though it is the correct way or a formalized way to name it. Right? So instead, a biochemist went through and said, well, I want to change my view on this molecule to simplify the structure. Right? And so the first thing that he did was change the orientation of the structure. He oriented it so the carbon chain was on the vertical axis. The next part is he oriented it so it was always away. Right? And if we're going on the vertical axis, our highest priority atom could be at the top or the bottom. He defined the highest priority to be at the top. Right? The substituents then aim either toward or have to aim towards you. If you've done all of those rules, every single substituent that is not on your main chain is by definition aimed at you. Okay, so what does that mean for our molecule? So there's our standard kind of line angle format. If we turn it, we'd see something like this. Okay, it's still zigzagged, which means as we go through and do this, you'll see some occasional wedges popping up. Okay? You'll also notice that to the left and right we have dashes. Okay? So we're not in the Fischer projection. We've just oriented it to that first rule. Okay? The carbon chain is on the vertical axis. We then have to go through, and every point where the carbon chain isn't aligned the way we want it to, we'll rotate. So if we start from the top, it's oriented exactly as we want. The carbon chain is by definition dashed going away. The substituents are wedged to either side. Perfect. But if I move to the next position, what's the problem? Well, this position is wedged and these are dashed. So that's not right. So what he went through and did is said, okay, that means I need to rotate this bond. And when I rotate that bond around, it becomes that. Now it looks better. Okay? And better is an arbitrary word. As we continue to move through the chain, we continue to do the rest of those rotations, and we would end up with this drawing. Okay? And you might wonder, well, how can every single carbon bond be dashed going away? That makes no sense. Okay? What's happening is we're changing our viewpoint from carbon to carbon to carbon to carbon. So as we're drawing the structure, we're literally rotating the molecule, okay, to redraw the structure in a new view. Why? Because then we can make this drawing. Okay? If we change our viewpoint on it, really what's happening is we've folded the structure back on itself. Okay? Where that carbonyl is closest to you, and this is now spiraling into the 7 depths of hell, okay? Going away from you. If we look at our molecule, okay, as we spiral around, from here, well, the carbon backbone is going away from me then, right? Where would the OH be? Well, it's going into the plane, which would be on the right-hand side. There it is. That OH is on the right-hand side. If I move to the next carbon, I'm now changing my viewpoint, and I'm now looking from down here. The carbon chain is going away from me. The OH is coming out of the plane, which means if I'm standing here looking up at it, right, it's on my left-hand side. Okay? If we go through and look at the drawing, there it is, OH on the left-hand side. Okay? For those of you who don't believe me, that's fine. You can either choose to just accept it or build the model, and you will see that I'm actually right. Okay? It is insanely frustrating for anybody that's trying to manipulate these things, but the intent behind it is a pretty legitimate one. Because what happens after all of this is I can now go through and say, I'm in this viewpoint. I'm now a Fischer projection. And because I know I'm in this orientation, all of those dashes are now part of the definition. All of those wedges are part of the definition, which means I don't need to show them. And I can simplify my structure down now into just this kind of fishbone-ish looking diagram. Okay? Sometimes referred to as the bow tie orientation. Okay? A bit silly because when we look at the Fischer projection, it doesn't look like a bow tie, but if we include the wedges and dashes, that's where we see the bow ties. Kind of make sense? Okay? This gives me a cleaner view of the molecule, and depending on what I'm trying to do, is potentially easier to manipulate. Okay? Some things that kind of come out of this. Assigning R and S can become tricky. So let's go through and take a look at the first position, or first chiral atom. And if we went through to assign priority to that, oxygen is the highest priority, right? So we'd go 1. Hydrogen would be lowest priority, 4. And then we'd have carbon versus carbon, right? So where would our higher priority be, top or bottom? It ends up being the top. There are two big answers for why it's the top one. Fischer, by definition, said the highest priority is at the top, so that kind of works within our carbon chain. The other way to look at it, that carbon goes out to an oxygen. Well, so does this one. Remember, it's a carbonyl. It's going out to a second oxygen, whereas the bottom carbon is only going out to carbon. So the top one gets the higher priority of those two. 2, 3, if we assigned 1, 2, 3, right? That looks like we'd be assigning that as S, because that's going counterclockwise. But, what's the but? It's not. Okay, we can do better than that. Hydrogen, our lowest priority, must be aimed away from you. Because it's a Fischer projection, where's that hydrogen aimed? At you. So we're looking at it backwards. That's not S, that's R. So the S got switched to R. If we go through and do the next one, we'll end up with 1, 2, 3, 4. And we would go through and say 1, 2, 3, right? Which looks an awful lot like, that's still S, right? Is that S? Oh, helps if you number right, by the way, just for the record. I got 1, right? You know, 1 out of 4 ain't bad. The hydrogen was the 4. That one's 2, that one's 3. 1, 2, 3, which would say R, but I'm looking at it backwards, so it becomes S. Okay. The next one is R. The next one is R. How did I predict those? Okay. I could look, the next two are R's because they're the same as the top. Did I actually have to count out the blue one to get S?
No, you could just see it was the opposite.
I could have just seen it's the opposite of the first one. Okay. R stands for
Reverse.
Ooh, reverse isn't a bad idea, but no. Didn't think of that one. Right. S being sinister for left. Where's the blue one located? On the left-hand side of the structure, and that one got called S. Where's the R one? All on the right-hand side of the structure. Fischer's orientation or reorientation of this can make us kind of go through and say, well, I don't have to worry about this RS stuff because I can say if it's on the right-hand side, it's R. If it's on the left-hand side, it's S. I just simplified drastically that process of assigning R and S. Okay? Don't get it, that's okay, because you probably won't see it. Okay? It shows up maybe once on an exam. Okay? So that's kind of a neat little process to go through and do. Fischer organizes this and simplifies nomenclature for biochemists. Okay? When we scale up to molecules that are now so complex that we don't want to use the standard nomenclature rules. Okay? When it comes to nomenclature, that's about as good as it gets in biochemistry. Everything else is effectively named after whatever arbitrary thing they saw. Okay? So I know I use pineapple and goats fairly frequently. Yeah, we get names that are that ridiculous. Okay? R and S determination. Right? We just went through and did that. We can assign as the normal priority and then just change to the opposite. That would be the way that I would recommend to do it because we maintain the same pattern. Or we assign highest priority on our bow. On the right-hand side is R, left-hand side is S. Okay? You will notice that if you move into biochemistry or if, say, you're studying for an MCAT or anything like that, you may hear words like D or label systems as D and L get dropped in there. Capital D and capital L. Nothing to do with R and S. Absolutely nothing. Okay? D and L are now in reference to this position and saying, where's the highest priority group? If it's on the right-hand side, it's D. If it's on the left-hand side, it's L. Aren't there other chiral atoms? Yes. This is where the nomenclature system comes in to address those other chiral atoms. Okay? When we're looking at carbohydrates, we start the simplest with 3 carbons, and we can work all the way down to what, 6 carbons? 6 carbons. Okay. If you notice, each of those has a slight switch within the OHs. Guess what? Each of those gets named something. As a biochemist, you're responsible for knowing what those names are. Sweet. That's about all I want out of that. Okay? So, physical observations, diastereomers. Okay? What are their physical properties? Okay, so like melting point, solubility. If I compare these two structures, would I expect them to have the same physical properties? They have the same intermolecular forces, but do they have the same shape? Okay? It can help if we switched over to, say, a Hayworth. Okay? And in the Hayworth, we can see that we have perhaps our ring, one up and one down. And the other one, we have them both up. Is that going to change how those molecules interact with other molecules? Yep. Which means their physical properties are different. Okay? Which means anything that we do in the lab would allow us to differentiate these because they have different intermolecular forces. That's pretty awesome. So diastereomers are not a big deal. Okay? And in fact, relatively easy to work with. Okay, how could we identify which one was made? Anybody in the lab should be able to answer that. We could use spectroscopy. Okay, we haven't officially-ish done that, sort of. Yeah, we did in lab. What else could we do to identify? You could use TLC to compare to a standard. We would expect different travels for these on TLC because their intermolecular forces are technically different due to the structure. What else could we do? Melting point. Okay? All useful identification techniques. Okay? For those of you working on the TLC lab, you might rethink some of your answers. Physical observations. Let's drop in the enantiomers. Okay? What happens if we look at a pair of enantiomers? So on the top, we have S-naproxen and R-naproxen. Okay, S-naproxen is an anti-inflammatory. Cool, that's like our pain reliever. Neat. R-naproxen destroys our liver. Okay. When they make naproxen, they have to be very careful to remove the R-naproxen because we don't want to go have our customers have cirrhosis. Right? Cirrhosis? Does that work? Yep. Thank you. Okay. We take a look at R-limonene. Okay, R-limonene's over here. Okay. Very subtle difference in those. In fact, I highlighted it by keeping the dashes here. What changed between those structures? The location of the double bond, be it on the left or right-hand side of the structure. Really simple change. R-limonene smells like citrus. Oh, that smells kind of nice. Okay. You will do that in the lab. For those of you in lab, some people call it citrus vomit, so it's not that nice, but it's not horrible. Okay. S-limonene smells like turpentine, which is not a particularly nice smell. Okay. Significant difference in scent, and all we've really done is just changed the location of one double bond. Carvone, okay. Personal fan of mine, or I was a personal fan of carvone because we could try to make those two convert. R-carvone smells like mint. S, caraway. Okay. Mint is a like greeny kind of like herb for your mojitos. Caraway is not. Caraway is like your rye bread. Okay. Those are some pretty distinctly different flavors. Okay. And again, subtle change in the structure. Okay. So we run into a big issue with our enantiomers. Okay. While they have different appearances to us, that is because we are chiral. Our noses are chiral. Our taste buds are chiral. So when those individual molecules come in, due to the chiral mismatch, they taste or smell like different things. But in the lab, we aren't dealing with chiral substances. Okay? Which means these species exhibit, to exhibit different melting points, they would need different forces. The problem here, all the forces are the same. Okay? They're mirror images of each other. So within a single enantiomer, how they stack and interact with each other is identical, which means the melting point for S-naproxen is the exact same as the melting point for our naproxen. Right? I could use melting point to tell me that I had a mixture of both, because when I mix them, what would happen to the melting point? It should now drop and get a broader range, because it's now impure. Right? How would I go through and separate these? Well, if I use just a simple system like we've been using so far, they have identical forces, which means they have identical relationships with solvents, they have identical relationships with our TLC plates, and they become inseparable. Oh, well, that's not a big deal. I'll just make sure that when I make naproxen, I give everybody the S and the R. Right? They won't have to worry about their headaches anymore. And I won't have to worry about them complaining, because they'll be dead. Right? That's kind of a bad business model, because the people that survived come back and kind of hunt you down. Right? So we need to come up with some way to deal with enantiomers and how to separate them. Okay, so how can we go through and do this? Well, rule number 1, don't make them. Okay? So when we go through and design our experiment, we'll look at our reaction conditions to make sure that we don't make pairs of enantiomers. Okay? That is not a super easy thing to do, but death versus life is kind of an important thing to do. Right? And because it's so difficult to separate them, we just try to avoid making them altogether. Okay? After that, instead of using an achiral solvent, which most solvents are, we could use a chiral solvent, okay? Or a chiral TLC plate to allow us to separate them away from each other. Okay? Those tend to be expensive, okay? Which is, again, why we don't deal with this. Okay? The next one, react both with a chirally pure compound and then separate like you normally would. Well, it seems kind of weird, so let's go ahead and take a look. We've got two compounds here, enantiomers of each other, right? Just say yes. Yes, thank you. Okay. If we went through and assigned R and S, right, this first one, 1, 2, 3, hydrogen aimed away, this would be 1, 2, 3, right? And I'd have, isn't that R?
R, yeah.
Okay, sorry. I get it backwards all the time. 1, 2, 3. Well, that's the same thing. I thought it said they were enantiomers. Hydrogen being 4 is aimed at you, so we're looking at it backwards. We'd have to flip it, so that one becomes S. Okay. So now it says react with a chiral pure compound. The chiral pure compound that's typically used is tartaric acid. Okay. This goes all the way back to, again, I think Pasteur, the whole wino playing with chiral crystals. Okay. Wine produces tartaric acid, and the crystals are very easy to separate from each other visually, so you can actually hand pick them out. So we could then hand pick those out and now add these in. Okay. What happens? Well, I generate and make a salt. Why would that help me separate them? What salt did I make? What is the relationship between... I thought it said what was the relationship. This one's R. This one was S. If we go through and look at our products, we have R. What did the tartaric acid bring in? What did the tartaric acid bring in? R. The other one was S. R. What is the relationship between those structures? Now they're diastereomers. Because they're diastereomers, their physical properties are different, and I can now physically separate these. Right? How do I reverse the process? Right? Well, what kind of reaction happened? Like, we haven't talked about anything in OChem. That's because you guys should know this reaction because you've done it in Gen Chem. It's an acid-base reaction. All that happened was a transfer of a hydrogen. Oh, that's going to bother me. I can't do that. Was a transfer of a hydrogen. Right? So it's an acid-base reaction. How would you undo an acid-base reaction? Well, if it was an acid to begin with, add a base, and we reverse the reaction. Okay? So that's a common question that pops up on looking at how to separate enantiomers. Okay? Looking at reacting them with a chirally pure compound, tartaric acid happens to be the most common one. Okay? Last but not least, accept that you suck at it and just tell everybody you screwed up. Okay? So report the excess. Okay? So what we would go through and do is define an enantiomeric excess. And what that means is I would say the percent of the highest enantiomer minus the percent of the lowest enantiomer. Okay? If I made both of them in equal amounts, what would my enantiomeric excess be? 0%. I did not favor one over the other. If I made only the R and none of the S, my enantiomeric excess is 100%. Okay? So it's just looking at manipulating those percentages and trying to define it. Okay? Which brings in the next kind of issue. We have to be able to determine how much of each of these enantiomers we have. Well, if they don't separate away from each other, how would I figure that out? Spectroscopy. Okay? That's our separation, or not our separation scheme, but our identification scheme. Right? So we can take our sample and we can drop it into our sample cell, and it surprisingly interacts with light differently than most samples. Okay? We have to make sure our light is polarized, so we use a filter that removes half of the light. Okay? That then leaves me with just one axis of light. That one axis of light, when it hits the sample, will now interact and rotate. Okay? Which way does it rotate? Well, it depends on the enantiomer. Okay? And one of the things that people like to go through and do, but we need to be hesitant about, is say, well, R meant right or clockwise, so that means if the light rotates clockwise, then it's R, and that's our dextrorotatory, or R+. And unfortunately, we couldn't be more false. Right? R and S are an absolute configuration on the structure. Optical activity is an assignment of our chirality based on a black box. I can't see what's in it, I just see that it rotates light differently. Okay? Which means if I have an R enantiomer, it could rotate light to the left, it could also rotate light to the right. We really have no way to distinguish. Okay? So treat them as different systems. Okay? The big point out of this is that every sample, or every chiral sample, will rotate light. Okay? So let's say we encounter a sample that rotates light to the left. What happens if I take the enantiomer? Interestingly enough, it rotates light the exact same, but the other direction. So enantiomers will rotate light the same magnitude, but opposite directions of each other. Okay? So you may see a structure labeled as negative limonene, right? Or positive limonene. What they're referencing is how that sample rotated light. Okay? This is not the same as R and S. I cannot emphasize that enough. Do not overlap these terms. Okay? That doesn't mean we can't use information from both, but they are not the same. Is there a question? Okay. Of course, we're now getting numerics in this, so we could run through calculations. Similar to Beer's law, where your absorption is related to concentration in the path length, we get a similar system happening here. Okay? The amount, or the amount of rotation is related to the amount of substance present and the path length of the sample. The longer the path length, the more likely your light encounters a compound, causing more of a rotation. Okay? Every compound that the light hits causes the light to rotate a little bit more. Okay? So that means higher concentrations means more rotation. We need a way to normalize that, just like a percent yield. And that's why we get the formula in the red box. Okay? We get our specific rotation which will be equal to our observed rotation divided by concentration times path length. Okay? You get some weird values that come in that. Concentration is grams per milliliter, and your path length is in decimeters. Okay? The other thing that's useful is we can get this other thing popping up, EE for dolphin speak for, somebody laughed, so that's good. I get that. An enantiomeric excess is equal to whatever your specific rotation was for your unknown system divided by the specific rotation for the pure compound. Multiply that by 100 and you get your enantiomeric excess. Okay? So that gives us a second way to calculate the enantiomeric excess, and we can use that to actually backtrack and determine how much of each enantiomer is present in a sample, which gets a bit tedious as far as the mathematics go. They really aren't that bad, but it often confuses students. So we'll talk about that in just a second. So before we get into that, let's get some multiple choice questions out of this. Which of the following show optical activity? Okay. If I have an R enantiomer, what does that mean? Do I have a chiral molecule? Yes. So what happens when the light hits the R enantiomer? It rotates. Which way does it rotate? I don't know. Okay. R and S are not the same thing as plus and minus. Do not confuse the two. So the R enantiomer will cause a rotation in the light. If the light rotates, we have optical activity because the light is acting as something. It's moved. It's changed its state. Right? How about a meso compound? What the heck was meso? Okay. A meso compound, we got a couple suggestions out here, was achiral. Doesn't it have a chiral atom? Yes, it does. Ah, but it has two. It has an internal mirror plane. So if one is R, what is the other one? S. So what happens when our light comes through and hits the R? It rotates. Wouldn't that mean it's optically active? It continues to pass through the sample until it hits the S, and because the S is the complete opposite of the R, the light rotates back. The net result being zero rotation. So a meso compound is now not optically active. Okay?
So a mixture of that is racemic?
We'll come to that in a second, a little bit. Okay? A mixture of enantiomers. Okay? 1 to 3, meaning I have 1 part S and I have 3 parts R. Would I expect that to rotate light? Yes. In this case, whatever way the R dominates or the R solution rotates, the bulk of my sample will rotate that direction. The S will cancel out 1 part and I'll have effectively 2 parts R. And so I'll see some rotation accounting for that. Make sense? So that molecule is also, or that system, mixture, is chiral. Right? So as Cass was suggesting, that's a mixture. You're starting to say, well, mixtures then are racemic. No. Okay? Racemic means something very particular. Okay? Racemic is in place of this last one, or this next one. A mixture of enantiomers, 1 to 1. Very similar to the meso compound, my mixture is now achiral. So if my mixture is chiral, I see optical activity. If my mixture is achiral, then I see no optical activity. Because when we go through to run reactions, if it is possible to generate enantiomers, we usually are stuck producing both. So instead of going through and labeling that mixture as a 1-to-1 mixture of R and S, okay, or 1-to-1 of enantiomers, I can label that system by a new name. That new name, as Cass was trying to suggest, was racemic. Okay? What if I have a racemate? Then I win because I'm faster than all my friends. What is racemate? Racemic is an adjective. Racemate is a noun. Right? They're different word conjugations. English does that, right? So they're just conjugations of the same word. They're meaning the same thing, just applied slightly differently. Right? So you may see a bunch of different terms come out with racem something or other with the suffix. They're all referencing the same thing. We have a one-to-one mixture. How else could I, actually we'll look at the last one. A mixture that has a 0% enantiomeric excess. What does that mean? Well, what was enantiomeric excess? Okay, it's the percent of one, we'll call it positive, minus the percent of the other, minus. If I have a 0%, what is the percent positive and the percent negative? 50-50, which by definition means we have a racemic mixture and we have no optical activity. Make sense? Okay. I know pictures just got taken there, but let's go through and circle the ones that are important. Which of the following show optical activity? A does and C does. That's it. Yes?
Just to clarify, B is not racemic, technically.
B is not racemic.
Okay.
True. Racemic is referencing two compounds. Good question. Racemic is always two compounds.
Is racemic always 1-to-1?
Yes. By I think people are playing fast and loose with the definition when they start using racemic other than 1-to-1. It should be defined strictly as 1-to-1. Other questions? Okay. So let's take a look at what we got here. Bunch of formulas, so you can already start to panic a little bit, okay, unless you really like Gen Chem. The specific rotation of 2s iodobutane is plus 15.9 degrees. Determine the percent composition of an enantiomeric mixture of 2-iodobutane if the specific rotation for the mixture is negative 3.18 degrees. Oosh. So what kind of information could we needle out of this without having to do any work? Which enantiomer do you think is in excess? Why R?
Since S is positive, R has to be negative.
S is positive, which means R is negative. Since the value I'm getting is negative, the one in excess is probably R. That's why it's coming out as negative. Or something just really oddball is happening in the question, and that's just me. Okay. Do I expect a lot of R to be present? Okay. What's the relative ratio you think between these? 100% R? Why not 100% R? If it was all R, what would its rotation be? Negative 15.9. Remember, enantiomers rotate light equally. Right? Just opposite magnitudes. It is not negative 15.9, so it is not 100% R. That value is actually starting to approach what? I'm hearing 2 and 1s. I'm kind of confused by that. I don't know what that means. I would say that's getting darn close to 0, which would suggest the percentages of each of those in the mixture are pretty close to 50-50. Right? Not perfectly, but the R should be in greater excess because we see a negative value out of this. Okay? Could we go through and calculate this? Yes. Do you want to? Have at it if you want to. I don't want to calculate it. If you would like to talk to me in lab about how to go through and calculate it, we can. Here are some hints. Okay? Big concepts, S and R and plus or minus are unrelated. Right? When I go through and solve this, I do make a substitution for plus and minus because those are also mathematical numbers. So I tie, within the question, we've got enough context to tie S and R to plus and minus. So I would tie those in so that I don't worry about the mathematical relationship between plus and minus versus the name relationship of plus and minus. Okay? If it is pure S, then 15.9. If it is pure R, then it's negative 15.9. If I take the amount of S, the percent of S, and the percent of R, what would that then add up to be? That is not the enantiomeric excess. Enantiomeric excess is the one in excess minus the one not. What is S plus R? Not total rotation either. It's easier than that. Not pure R. What is the percent of S plus the percent of R? It's 100%. That's what percents mean. If there's two states and I add the amounts of those two states, it had better equal 100%. Right? That last little equation is the part that everybody seems to ignore. With that information in the equations above, you can figure everything out, okay, if you would like to. Other than that, what we talked through in it on what can you draw as conclusions without actually having to solve, that part's important. If you want to go through and solve anyway, if you see a question on the exam like this, then go ahead and do so, but you do not need to solve. You need to be able to interpret. Okay? So that ends our first sort of category on spectroscopy and sort of gets us out of chirality, right, which now gets us into how do we prove our structure. We really have four forms of spectroscopy. UV-vis spectroscopy, which believe it or not will finish today. IR spectroscopy, which hopefully will also finish today, but we'll see. Mass spec and NMR. Okay? The first three should be treated very, very quickly, the IR being the most important of those first three. NMR is the most difficult. It takes the most practice. Okay? Believe it or not, what I had you do at the beginning of this class, going through and trying to really quickly assign, is what you need to be doing. You need to pick up that skill quicker. Okay, so let's take a look at what's happening. Okay? Pretty much all of these center on the electromagnetic spectrum and looking at the different molecular effects that can come out of different waves of the electromagnetic spectrum. Right? So we're looking, in some cases more than others, at the relationship between each of those components. Right? If we look at the UV to visible, we get electronic transitions. That means electrons jumping from orbitals. This is why when we put 20,000 volts through a gas of an element, what do we see? Cool colors, neon lights. Right? Those are electronic transitions. IR is your molecular vibrations. Microwave and radio get into rotational motion or nuclear spin transitions. Okay? Not enough energy to cause things to really move, just cause them to spin a little bit or wiggle. Okay? Each form of spectroscopy takes advantage of one of those sections. Okay? So ultraviolet and visible light. We're looking at electronic transitions. So we have a molecule. Where are the electrons in our molecule? Okay, if I had an atom, where would my electrons be? Around the nucleus. Touché. Give me a little bit more detail than that. Orbitals. Okay, we could call those orbitals atomic orbitals, and we could label them 1s, 2s, 2p, 3s, 3p, 3d, right? Okay. Can we look at the orbitals for this molecule and reference our atomic orbitals. What does atomic mean? Atom. Can we look at this molecule and reference our atomic orbitals? No. What do we have to reference? Our molecular orbitals. You mean the whole sigma, sigma star, pi, pi star? Yeah, exactly. That's what we're using. Right? So what we would do is look at a molecular orbital diagram for this compound and say what electrons are going to be excited. Right? Just like with our atoms, the electrons that get excited are going to be the highest energy electrons. Okay? We likely won't be able to detect electrons jumping from the bottom energy level to an empty orbital because the photon of energy would have had to pierce all the way through the atom to make it there. Odds are that's slim. So more than likely what we are going to be seeing is electrons in the highest energy level jumping to the lowest unoccupied energy level. Right? So if we look at this molecule, what would we expect the highest energy molecular orbital to be? Give you a hint, there's two types of molecular orbitals we should be looking at. One begins with S, and the other one begins with P. I'm hearing reference to hybridization. Hybridization, while it does begin with S, is not the name of a molecular orbital. It is the name of an atomic orbital. What would our molecular orbital be if I took an sp2 carbon and bonded it to an sp2 carbon? If they're sp2 carbons, they're bonding. The first interaction is sigma. It's the overlap of the s orbitals of our sp2 hybrid. Right? That's what our s was helping us with. Okay? Those are a direct overlap. Is there something higher in energy than the direct overlap of our sigma orbitals? Our p orbitals that contribute to pi bonds. Do I have pi bonds in this structure? Yes. So what I'm looking at is the electrons in the p orbitals getting excited. Okay. They're going to get excited and jump to the lowest unoccupied molecular orbital, okay, which would typically be our pi star, our anti-bonding p orbital. Okay. It turns out that the energy gap between those two happens to fall pretty much smack dab in the middle of the ultraviolet and visible light spectrum, which is why we refer to this spectroscopy as UV-vis. So what we are exciting is the electrons in pi bonds. What if your molecule doesn't have pi bonds? Don't use UV-vis. UV-vis is almost exclusively for pi bonds. Okay? Not perfectly, okay, but that's where it has its utility, is molecules with pi bonds. Okay? Those are what get excited. So if we looked at a UV sample spectrum, what we would do is we would scan from 200 nanometers up to 800 nanometers. We're scanning wavelength. Okay? Wavelength relates to energy. How? Shorter wavelength is higher in energy. So this low number, we're getting a lambda max. So the wavelength where we see an absorption is now our lambda max. Okay? That is now saying that our molecule absorbs light at that wavelength, which we could correspond to energy being, as far as our UV-vis, highest energy possible for this scale. Okay? This does tie all the way back to the Beer-Lambert law, which you should remember from Gen Chem. If you don't, there'll be 20 questions on calculations using Beer-Lambert law. That's a complete lie. I don't remember much about Beer-Lambert law either. Okay? I just remember the formula. Okay? So our sample, our absorbance, is related to an extinction coefficient, okay? A constant for each individual compound. Where does it absorb? Okay? The path length of our sample and the concentration again. Okay? So what can we do to use this? Well, if we go through and look at our diagram, what we've got is our ground state for the molecule, shown on the right with the red arrows. Okay? We've got our highest occupied molecular orbital. And when I fire ultraviolet light at this, that can cause an electron to get excited and jump. More than likely, it would jump to the lowest energy unoccupied molecular orbital, or our LUMO. That difference in energy now gets shown, or that difference in energy can get related to our wavelength, and that's when we would expect to see a peak. Why do we not see peaks anywhere else? Because the gap in energy between those doesn't correspond to the gaps that we see there. Okay? So we could do all sorts of fun mathematics behind this, and it's not that big a deal, so we don't want to do that. Okay? What happens if we looked at an orbital diagram for 1,3-butadiene? Okay? How many sigma bonds do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma, which means I have 9 sigma bonding and 9 sigma star are anti-bonding. Higher in energy than our bonding would be our sigma bonding would be our pi. We have 2 pi bonding and 2 pi anti-bonding. Did I write anti for the first one? Yeah, I did. Right. And if we went to place electrons in, what we would notice is that our highest occupied electrons would go into the 2 pi bonding. When we fire light at the molecule, those electrons can jump to the anti-bonding. To do that, they had to absorb light, which means we can detect the loss of light when we use our instrument. Okay? The textbook shows a nice pretty picture, which I'm sure you love, but that's what it's showing. Right? There's our 2 pi bonding. Our electron, or our energy comes in, hits the highest occupied molecular orbital, and the electron jumps to the anti-bonding. That is now an absorbance that we can detect. That is the most likely jump to be made. Okay? Other jumps are possible, they just are less likely. Okay? Why would they be less likely? They are probably more energy. Could I excite the electrons in the pi bonding, or the pi 1 instead of the pi 2? Sure. What do I have to do to get to the pi 1? I have to get by the pi 2. The odds of that happening now start to drop. So it's less likely to see those other transitions. Okay? So our focus sits at that HOMO to LUMO jump. Okay? What happens as we add more electrons? Okay? I know this one gets a bit jumpy, but ethylene, single double bond. 1,2-butadiene we just looked at, there's our 4 molecular orbitals. What happens when we move up to hexatriene? We get 6 molecular orbitals. Okay, 3 pi bonding and 3 pi anti-bonding. Anybody notice anything interesting about what's happening between the HOMO and the LUMO? Okay, so we could talk about the nodes. Yes, the nodes are there, but I asked HOMO to LUMO, which really means what can I do? I can ignore all of those images. And what I'm talking about is the HOMO to LUMO, the HOMO to LUMO, the HOMO to LUMO.
So is the smallest energy gap?
It's the smallest energy gap. I accept that as a pattern. What else is a pattern? It got smaller. The more double bonds we put in conjugation, the gap got smaller, which then means the energy shrinks, which means we go from ultraviolet to violet, or ultimately, less specifically, visible. Right? If you think about the colors that you see every day in your clothes, this is why. The dyes used to make the colors in your clothes, most of them are organic dyes. We see the colors that we do because the dye is absorbing energy, preventing us from seeing that wavelength of light. Okay? Kind of neat. As everybody starts looking at their clothes. Like, really? Yes. Okay? So, quantitatively, we could drop in and look at some numbers. Let's take a look at some comparisons here. So, remember, it's just the double bond that generates this. Let's take a look at ethene, right at the top. 161. That's where we see our lambda max. So we're saying it absorbs at 161. What happens when I move to hex 1-ene? It changes a little bit. Okay? Would I expect it to change? Yeah, why? I have more carbons on it. Those carbons can affect the double bond. What happens when I move to penta 1,4-diene? 2 double bonds. I should see a difference here, right? What happened to the number? That's not much of a difference. Why is there not much of a difference there? Kind of has to do with symmetry. Have we changed the energy of the pi bond? When we move from hex 1-ene to penta 1,4, has the energy of an individual pi bond changed? So there's a double bond bonded to 1 carbon. Penta 1-diene, what do I have? There's a double bond bonded to 1 carbon. What else do I have? A double bond bonded to 1 carbon. Have I changed the energy of the pi bond? No. Yes, I have more double bonds, but those double bonds all have the same energy, which means same wavelength. Okay? Is there a way that I could have put the 2 double bonds in such a way where they can now interact with each other? Okay. How about we look at this one? Can those double bonds interact? Yes, through resonance. Okay. What happens to the wavelength now? Wow, that changed significantly. We're looking at a big jump there. So when our double bonds come in contact with each other, that significantly changes their energy. That's when we'll see a change in the lambda max. Okay? As we continue to conjugate, we continue to see that wavelength jump. Okay? Which is kind of a neat feature of our lambda max. And that's, whoa, the big, actually it's here, the big summary that we want. Increases in conjugation cause an increase in lambda max. That's the big lesson of UV-Vis. Okay? The more double bonds in resonance, the higher the lambda max becomes. Okay? Good timing if you just woke up. We good? Okay. IR. Okay. There's a lot of stuff, again, floating through IR. Our typical range for when we're looking at IR is 4,000 inverse centimeters to 400 inverse centimeters. Why are we using inverse centimeters? Good question. I don't know. Okay. Because we liked negative numbers and we liked exponents, right? Everybody loves those. Okay. It ties back to our energy. Our wave number is technically 1 over the wavelength. That's why we have our wave number. Okay, and that's what they'll reference it as. Okay? So some big important relationships. As the energy increases, our wave numbers will also increase. So this is kind of nice. We can evaluate the energy of a bond and say the more energy it has, the higher wave numbers it has. Okay, that's a nice little correlation that we can use later on. So what is IR? Okay. IR is all about bond vibration. Okay. Lots of different bond vibrations as this image shows. You can get stretching functions where they're just on one plane, oscillating back and forth. Okay. If we add in other things to this, okay, if it's still just 2 points, my hand and my shoulder, yes, I can have a stretching function. I could also have one where it kind of bends, right? Okay. That adds another type of vibration. Well, that type of vibration requires a different energy, which means a different peak in our spectrum. Okay. As I add more atoms into my molecule, I'm going to get all sorts of other types of vibrations. Okay. That's what they're showing down at the bottom. If we now look at 3 atoms, we could get a symmetric stretching, we can get an asymmetric stretching, and then we can also get a bending. Okay. All of those correspond to different energies, which means a different signal in our IR. Okay. There are tons of possible vibrations for any given molecule. Okay. The ones that you're going to be most concerned about are the stretching vibrations, or the stretching modes. The rest are important, but they get convoluted or confused with a bunch of other signals, so we can largely ignore them. Right? The other big thing on this, bonds. Okay? So the simplification, I only want a single bond. I'm looking at 2 atoms in that bond and how the vibration changes for those 2 atoms and those 2 atoms alone. This means when you go through to analyze an IR, be very careful in your analysis to only evaluate as a bond and not as a larger functional group. Okay? Which can be tricky because there are some signals that students like to jump all over as saying they're a particular functional group. They aren't. They're a bond. Okay? Some general patterns that can come through this for our stretching frequencies. Your frequency decreases with increasing atomic mass, okay, assuming your bond energies are the same. Your frequency will also increase with increasing bond energy. Okay? I spent some time poring over this, trying to come up with some kind of broader analogies through this, and there's not a lot of easy ones. Okay? So simplify it down as much as possible. I think the bond energy is the easiest. As we move from a single bond up to a triple bond, what happens? Well, the bond got stronger. What happens to the frequency? It goes up, goes to a higher energy, because there's more energy in that bond. Okay? That can help as a rough approximation, but it really isn't all that big of a deal, because ultimately what you should be doing, sorry, still not quite there. We got a little bit more theory to go through. What you're detecting is, again, the asymmetry in this. Even a symmetric stretch is testing for asymmetry. Okay? You can tell where my hands are going relative to my body because my body looks different than my hands. Okay? If they all look the same, it becomes very different or difficult to detect the stretch. Right? So what we're looking for are dipoles. The further away the atom gets, the larger that dipole, or the larger difference we see there, the easier it is to detect. This is why bonds like OHs or carbon oxygens, okay, or even carbon nitrogens, tend to be very intense signals. Okay, because there's a large dipole, because oxygen is very electronegative. But if you switch to, say, carbon-carbon or carbon-hydrogen, those bonds tend to be weaker in intensity because there's less of a dipole. The tricky one, I know, just let me finish here. You can encounter molecules that have a 0 dipole moment, or even bonds that have a 0 dipole moment. This means that the IR cannot see them. Okay? The biggest example of this is the triple bond. Shows up every so often. If I look at a carbon-carbon triple bond, the triple bond, for those of you that have been reading ahead, show up at 2250. But if I go through and put a carbon here and a carbon here, that triple bond disappears. Because the molecule is now symmetric, I can't detect the bond anymore. So there are bonds that are IR inactive. It centers on the idea of the zero dipole moment. Okay? So the biggest one there is that symmetric triple bonds. After that, what we'll talk about on Wednesday is pretty much all the things you need to memorize for IR. We'll talk about mass spec, and then we'll move into NMR. Hopefully we'll actually get into NMR on Wednesday. Yes, this is a lot. This is why you need to watch those videos. If you don't watch the videos, that's fine. You got a lot of textbook reading to do.